I will show you everything you need to know about functions in machine learning. This is extremely essential part, and even if you think you know about functions, I really recommend you watch this video because I will show you how it applies to large language models, to neural networks, and machine learning. Hello guys, this is part of my private course to become AI researcher. It's just $9 per month and you have 7 days free trial. So I'm gonna release one lesson right here so you know what it looks like and decide if you want to join. Function takes some number and transforms it into some other number. And it will always just transform into a single number. It cannot transform one number into multiple numbers, just single. So just one to one. So for example, if we have function f of x, or this can also be denoted as y. So f of x or y is the same. F of x is equal to 2x plus 3. Let's see, if x is equal to 0, then f of x will be 2 times 0 is 0, plus 3 will be 3. So let's see here. If we see x is 0, let's see this here where this line intercepts. So when it's here 0, here it should be 3, and it is 3. Because this here is y-axis, this is x-axis. So this is y or f of x-axis. So let's say x is equal to 5 here. So if we calculate 2 times 5 is 10, plus 3, 13. Let's see. So 5 goes here, and if we check, yeah, this is 13 here. I recommend you also copy this text and use it in a ChatGPT or some AI chatbot and ask questions. It's like a personal teacher, so you can follow me and follow my tutorial as well. So if I say something that's confusing, of course you can ask that here as well, but maybe you will get instant response in a ChatGPT or AI chatbot. Here below, I showed you step by step how these functions are calculated, so you can check that if you want. We also have quadratic functions. Now you see that linear function, so there is no square or cube or exponent on the x. So this function is linear. But this function that has square on the x, this is a quadratic function. And this is what it looks like. So it's no longer linear. You see now it's curved. So now, actually as x grows, y grows a lot faster because y or f of x is actually squaring. So if you check some numbers, the squares grow a lot faster than linear. So if you go x to be 1, 2, 3, 4, the squares of those numbers will be 1, 4, 9, 16. So it grows a lot faster. Here in the beginning, you see it's actually a bit it's not growing so fast. But here towards the end, it starts growing like going up very fast. Here it's not going up so fast, but here it's going up very fast. So you can check the slope. Here it's almost like there is no slope here at the bottom. And then slope is increasing slowly, and the slope is going to continue to increase in a square function forever. The slope will be, it will never be 90 degrees though. It will always be approaching 90 degrees. So it starts like this and it starts approaching 90 degrees, but it's never going to be 90 degrees, the increase. The slope, I should say. So by the way, this function goes on forever. This image just isn't showing it because I cannot draw a forever function, but it goes on forever. So it shows until 10, but even if you put 12, there would be 12 square here. Let's work out some example. So if we put number 5, you see, we say 5 square is 25, plus 2 times 5 is 10, so that's 35. Plus 1 is 36. So for x equals 5, f of x is 36. So 5, it should be 36 here, and it is 36. So you can say that function maps every element in set A to exactly one element in set B. So if you have something that maps one number to multiple numbers, that's not a function anymore. Function just maps one to one. So we call x input independent variable and y is the output dependent variable because y depends on x. So here, as I said, y, it's this f of x, that's y. So it depends on x, so it's dependent variable, and x is independent. Then I have this Python code. Now, if you didn't watch the Python lessons, then you can skip this for now and return to it later. But I will just copy this Python code and paste it into Google Colab. And you can see that this is our 2x plus 3 function. And so if we give it x, pass x to be 1, then it's going to calculate that f of 1 is equal to 5. F of 0 is equal to 3, f of minus 1 is 1, so it's just our function. You can play around with it. You can also copy this quadratic function and see how that works as well. I recommend you change this a little bit, maybe add plus 4 here, see what happens, plus 5, sorry. So now the numbers are going to be different. Let's check out types of functions. I already talked about linear function. So this is where we have x without having some exponent like squared or to 3. It's just like x. And there is nowhere in the entire function like exponents. So this is the code that I use to draw this image. So you can, if you copy this paste into Python, it will draw this image, but you don't need to look at this code. I'm not even sure if I should keep it here, by the way, but maybe I think I'll remove it. Here we have two linear functions. So 2x plus 1, which is the blue one, and minus 0.5x plus 3. So you see that this first number next to x shows the slope. So we have 2, this is a slope. If we have minus 0.5, you see the slope is kind of going in the opposite direction. So if we had even bigger negative number, it could go even like this, like even more. And positive numbers will move like this, the slope. And then this plus 1 or plus 3 will just shift left or right the entire function. So whatever your function is, this plus will just shift like left or right. This is a bit of function intuition, so if you don't understand this 100%, don't worry, everything will click eventually. You can now focus just on continuing tutorial and continuing to understand whatever you can. So if I say in this 2x plus 1 that 2 is the slope, it means if you move by 1, if you increase x by 1, y will increase by 2. So if you increase x by 2, y will increase by 4. You can also check that here, like see where this is here. So this is maybe 1. Yeah, it's 1. So if x is 0, y is 1. If x is 2, y is 5. So we increase x by 2 and y went from 1 to 5, so increased by 4. You can think about what I just said for a moment and rewatch it. Okay, another type of function is polynomial. So here is where we have exponents on our x. These are examples of polynomial functions, so they can be like very curvy. They have the general formula in this way. So a0, a1, etc. are these constants, these numbers, 1, 2, 3. So here there is also constant, but the constant here is 1. So this is same as 1 times x to the third power. So, and then we have x plus x to second plus x to third, etc. until x to n, whatever the number n just represents some number. So in this case, x goes from first, second, third. Also this one, there is also x here. This is x to 0. So x to 0 would be 1, just 1. So we have the constant 1 times x to 0, which is also x to 0 is 1. But we don't need to write x to 0, 1. I should zoom in like this, it's a lot more clear. So I'm just showing how to calculate this manually by hand. So you put x equals 1, and then you just put 1 instead of x and calculate everything. This example, this is the fourth power. You just put x equal to 1, calculate. And I wrote these two functions in Python if you want to run it, change it, play with it. And this is what they look like when you draw them. Exponential functions, this is interesting. This is when we put some number to the x. So a number to x. So 2 to x. E, which is Euler's number, to x. And this is what they look like. But this can be a bit confusing because this scale here is not linear. This is actually exponential scale here. So actually, as we go up on this y-axis, these numbers are becoming bigger and bigger, like exponentially bigger. It's not equal distance. It's like this much and then this much and then this much. So what I want, I will show you linear. So this is the linear example. So here y is linear, and you see what exponential function looks like actually. It's growing exponentially, so it's growing faster and faster. Then trigonometric functions. These are functions that have periodic behavior, and they are based on angles. This is its own subfield. I'm not going to be explaining this too much now, but this is something you will use. For example, this is used in positional encodings of tokens. So in large language model, when you want to tell the model the position of each token, which comes first, which comes after, you're going to use what's called rotary positional embeddings. And those rotary positional embeddings use these trigonometric functions to rotate vector embedding. Okay, I'm getting a bit ahead of myself, but I just want to show you that this is important, and not only there, in many other aspects. These functions are very important, sine and cosine functions. Now I have some specific functions that I want to show you. These are not types of functions, these are specific functions. So sigmoid function, this is what it is. And this is used in neural networks. And funnily enough, this is derivative of the sigmoid function, and we didn't learn what derivatives are yet. So I'm gonna skip this for now. So let's see what sigmoid function does and how it's used. You see here that first of all, for any x value, the y value will always be between 0 and 1. Oh, I can zoom in like this, I didn't even know. So and this will go on indefinitely. It will be approaching 0, but it will never get to 0. It will always be like a bit more than 0. And this will always be approaching 1, but it will never get to 1. So for any x value in the existence, in infinity, sigmoid function will always put it between 0 and 1. So this is good for neural networks. We want numbers to be 0 and 1. And if the number is 0, it will put it to 0.5. If x is 1, it will put it maybe here. This is maybe 0.75 or something. But that's the main property, putting it between 0 and 1, any number. And I'm going to tell you quickly what derivative is. So you see here, for example, here, there is not much slope. It's almost flat. So the derivative number there is very low. So derivative will tell you how flat or how much of slope there is. So this is actually very steep. So at this point, the derivative is very high. So it just tells you the steepness of the function at any point. So at 6, it's almost flat, so the derivative is very low. And this is how neural networks learn, but we will talk about that more later. ReLU, a very famous function, very quick, easy to calculate. This is used even in latest DeepSeek sparse attention paper, where they introduced new attention mechanism. It's very simple. If your x is lower than 0, y will just be 0. So it converts any number lower than 0 into 0. And if number is x, input is the higher, more than 0, it will just return the same number. So here for 1, if x is 1, y will also just be 1. It's a very simple, very easy to calculate function. It's not so powerful, but for example, in applications like DeepSeek sparse attention, where you don't need much compute for the indexer thing, whatever, the thing they calculated, we'll talk about that as well. You can use this simple, fast function. And this shows the slope. So here, there is no slope left of the 0. Slope is 0. But here, slope is 1. After 0, slope is 1. So it means like when I go from 1 to 2, when I move by 1 on x, y will also move by 1. So that's the slope. I want to actually show you what sigmoid function looks like. So it's 1 over 1 plus e to minus x. And this e is famous constant. It's called, I don't know in English, but we call this Euler's number. And its value is approximately 2.718. And we use that for sigmoid, next function I want to show you. So it's a bit different. But why do we use sigmoid? Sorry, tangent hyperbolic, not sigmoid. So this is similar to sigmoid, but instead of putting between 0 and 1, it puts between -1 and 1. So maybe sometimes neural network will perform better with this one, or you want to use it for some reason. That's it about functions. That's everything you need to know. And next, we're gonna go on to derivatives, gradients, vectors, matrices, and all the other maths you need for machine learning.